Today we are doing formula chart of chemical equilibrium and ionic equilibrium. So equilibrium, basically what is happening, rate of forward reaction will be is equal to rate of backward reaction. So at equilibrium, rate of forward reaction is equal to rate of backward reaction, means RF should be is equal to RB. So when we are writing with based on the mass action law, that equilibrium constant is a rate constant for forward and rate constant for backward. Or else you could write that concentration of the product and the power raised by the stoichiometric ratio. So if we have a chemical reaction, that is A moles of A and B moles of B will give you the C moles of C and D moles of D, and all should be in gas or the aqueous phase, then what you can do, that K, it could be the equilibrium constant. That equilibrium constant will be is equal to forward rate of constant by the backward rate of constant, or the concentration of the product and their power should be raised by their equilibrium constant divided by the reactant concentration, and their power would be their stoichiometric numbers. Today we are going to do the formula chart of the chemical equilibrium and ionic equilibrium, very important section of JEE and NEET purpose. So here we are going to cover the entire chapter in a glance and along with the formulas. So first, equilibrium means the rate of forward reaction would be is equal to rate of backward reaction. The RF should be is equal to RB. So if I'm going to write the reaction, any balance equation, that AA, will give you C moles of C and D moles of D. Then equilibrium constant, the K, we can write as a Kc or maybe Kp. That is, if I'm writing in terms of concentration, the Kc should be is equal to concentration of product by concentration of reactant and their power raised by their stoichiometric number. If I need to write that Kp, so that should be Kc, and the Kp should be is equal to partial pressure of C to the power C and the partial pressure of D to the power D and the partial pressure of A to the power A and the partial pressure of B to the power B. Remember that Kc and Kp is valid for the ideal condition. The container should be closed, no color change, temperature should be fixed. So Kp should be is equal to Kc RT to the power del Ng, where del Ng is represent, that is the moles of product minus moles of reactant only for gaseous substance, or else you could use the aqueous phase also. Here the K is only and only valid for the gaseous substance or else the aqueous one. That's it. Solid and liquid, it is not valid. Next point, if Kp or Kc is pretty higher than 1, means reaction is almost completed. Reaction complete. Generally 10 to the power 3 up, its reaction complete. If it is equal 1, means 50% complete. If it is pretty less than 1, means reaction just started and reach equilibrium. Next point, K is only, either it's a Kc or Kp, K only depends on temperature. Only depends on temperature. It is perfectly free. K is only depends on temperature. It is perfectly free from the initial and final concentration of the reactant. But obviously temperature can change the reaction. The catalyst, if I am writing, catalyst increase or decrease rate of reaction. So it only help to reach the equilibrium faster but will not change the Kc or Kp value. Reaction quotient, we have reaction quotient Q. If Q is greater than K, it means the reaction is backward. The reaction should go to the backward direction because at K value Gibbs free energy is negative. So reaction quotient Q or K, if the Q is greater than K, reaction goes backward. So reaction quotient Q, The Q value is basically product and reactant ratio at any point of time but not at equilibrium. If Q is greater than K, reaction go backward. Reaction is having the tendency to move toward the K. If they both are equal, this is at equilibrium. If Q is lesser than K, then again reaction has the tendency to move toward the K, reaction goes forward. If reactions are equal and opposite, you can see both are equal and opposite reaction. In that case, equilibrium constant is become just reciprocal of each other. K2 is become reciprocal of K1. If suppose I'm going to multiply the same equation by 2, B plus C, this is the K1, and K2 is I'm just simply writing that is B plus C. So K2 value is actually equal to K1 because both the reaction are same, only it is multiplied by 2. So for getting the second equation, I have to divide by the 2. So whatever the number you are using to get the second equation, this will go as a power. So you could write, if you are multiplying n number, the power will be n, or maybe, so if you are multiplying by any n number, the power will go as a n. Now formula of ionic equilibrium. So first we have a Oswald dilution law. Oswald dilution law is suggesting on dilution the degree of dissociation increases. So here if I'm going to use any binary weak electrolyte, it will convert into A plus and B minus. So in that case, that C00 at initial condition at T equal to equilibrium, it's become C1 minus alpha, and that is become C alpha and C alpha. So we have a K dissociation constant value. It's A plus B minus divided by AB, which is C alpha into C alpha and C1 minus alpha. So when you cancelling, so you will get the C alpha square. It should be is equal to C alpha square if the alpha is pretty lesser than 1. It should be is equal to C alpha square if the alpha is pretty lesser than 1, then you can ignore from the denominator. That Kw value is equal to H plus into OH minus concentration, which is equal to 10 to the power minus 14 at 25 degrees Celsius. So pH we can define as a negative logarithm of the H plus ion, and pOH is defined as negative logarithm of the OH minus ion. So we can write pH plus pOH would be is equal to 14 at 25 degrees Celsius. Salt hydrolysis formula, that pH should be is equal to 7 plus half of pK plus log C when we are using weak acid and a strong base salt. pH equal to 7 minus half of pKb plus log C if you are using that weak base plus a strong acid salt. pH equal to 7 plus half of pKa minus pKb if we are using weak acid and weak base salt. Important. And the pH would be is equal to 7 whenever we have strong acid and a strong base salt. Next is coming buffer solution. Buffer solution is two pattern, acidic buffer and basic buffer. For acidic buffer, you have pH is equal to pKa plus log of salt by acid, salt concentration by acid concentration. And for basic buffer, pOH would be is equal to pKb plus log of salt concentration by base concentration. pH can reserve their pH value, so the range for the buffer can reserve their pH value, so the range is for acidic buffer pKa plus minus 1, pOH is equal to pKb plus minus 1, and whenever they are on highest capacity, that is the salt acid ratio or the salt base ratio is become 1:1. So in that case, pH is equal to pKa, or else pOH is equal to pKb. This is the highest capacity when the buffer works. Buffer capacity is a number of moles of strong acid or strong base added in 1 liter buffer divided by their pH change. This is called buffer capacity. Solubility product is only valid for those electrolyte which is forming the saturated solution like AgCl. This is the solid. It's forming the saturated solution Ag plus and Cl minus. So equilibrium constant K should be is equal to Ag plus Cl minus, and now the name of equilibrium constant is called KSP, solubility product, and this section is called ionic product. KSP is greater than and equal to ionic product, no PPT will form, no precipitate form. But if it is lesser than the ionic product, PPT form. So this is all about the chemical equilibrium and ionic equilibrium. Hope it will be helpful. Like, share and subscribe. Thank you.